Hello everyone. This is Project 23031 for Design Day. We are the Autonomous Mechanical Spider Project, and our sponsor is Biosystems Engineering. The team members on this project are Ali Allah Q, Eli Bitsko, Tam Friedman, Caleb Lucero, that's me, Shambhavi Singh, and Ismail Zaki. We'd like to take a moment and explain why we're doing this project. According to the Food and Agricultural Organization of the United Nations, plant disease accounts for $220 billion in crop loss a year, with pests destroying an additional $70 billion. People have struggled against famine for millennia, but today we have a new tool. By a constant stream of information from interconnected devices, massive amounts of raw data can be analyzed, optimal decisions can be made, and commands can be distributed back out for machines to carry out. Applied to agriculture, data on crop health can be used to identify risks immediately, and countermeasures can be deployed in real time. However, current data gathering systems are inadequate for agricultural scale and environments. Static sensors require too many units to get close readings across large areas. Wheeled drones may work in urban areas but trample roots and crush soil and turf. Flying drones may also play a part in this information ecosystem, but lack loitering time, payload capacity, and the ability to examine samples beneath and in between foliage. This drone would be a foundation for future development, and therefore would be open source and made from open source software and consumer off-the-shelf parts, so as to be made as widely available for development as possible. We performed trade studies and found that using servos, with 6 legs that had 2 joints each, was the most economical design that allowed for the least unnecessary complexity. Now we will be going to the Engineering Design Center to hear about the design from some of our other engineers.
Hello everyone, my name is Eli Bitsko and I'm a mechanical engineer on the Autonomous Mechanical Spider Project.
So Eli, can you walk us through the robot?
Yeah, sure. So first off, overview of the entire robot is we have 6 legs. It's a hexapod, of course. Each leg has 3 degrees of freedom given by 3 motors. If you go into one of the legs, you see 1 motor right here, 1 motor right here, and 1 motor right here. Going more in depth, the CPU and main electronics of the robot are located in this housing under here. They're very safe. The auxiliary electronics, so things that drive our motors and read systems, are in this housing right here. The main battery is located up in this box right here. The payload compartment is right here. It can support a 10-inch by 10-inch payload and up to 8 pounds. And the LiDAR sensor, which allows machine vision and obstacle avoidance, is located right here on the front of the robot.
So tell us a little bit about how you made it easy to make and accessible.
I would like to point out that most of the 3D printed parts are optimized for 3D printing with flat profiles. They're basically just extrusions. They're very easy on a 3D printer. And every single component on this that is not 3D printed is bought off the shelf on websites like Amazon and McMaster. So if you have the funds and a credit card, internet access, and a 3D printer, you could go home and make one of these yourself.
Hi, I'm Ismail Zaki, and I am one of the mechanical engineers on the project.
So Ismail, we did a lot of analyses during this project, didn't we?
Yeah, conducting analysis was an important aspect of our design process, as this allowed the team to understand the requirements of the system and its behavior in response.
So what were 2 of the most important analyses that we did during this project?
Well, one thing we needed to verify was whether or not the motors produce a consistent error at higher torques, since this is what the system would experience during operation. And failure in verifying this would result in the risk in several mechanical failures, such as an even walk cycle, or even something worse, such as the legs crashing into one another. And our initial analysis of the motor feedback showed that there was a linear relationship between the servo motor angle and the potentiometer voltage. And because the motors acted predictably, we verified that they do have a steady state error at high torques. And knowing this, we could use available robot operating systems such as ROS2 control to reduce the error within an acceptable margin.
Now what about power?
So another crucial question we needed to answer was what type of power the system would require. And to answer this, we started by plotting experimental values of the torque versus the current across the motor. And using this data, we developed equations to relate the two. and we were able to quantify the expected power draw for each motor along the body of the robot. And then with this, we determined the battery we would need, the power converters we would also need to connect to the smaller electrical units, as well as how we needed to wire these components to the power subsystem.
Hi, I'm Shambhavi Singh, and I'm one of the electrical and computer engineers on the team. I'm particularly working with ROS.
So why did we choose ROS?
After doing a bunch of research on the kind of software that we could use for robotic control, we quickly concluded that ROS was our best bet. ROS stands for Robot Operating System, and it is an open source intermediate software that provides integration for hardware devices, simulation for movement, robotic control, localization, and other algorithms for path planning and actuator control. One of the reasons is that ROS is great because it's highly modular and has a variety of packages and drivers made by the community to handle a variety of devices.
How did we get ROS to work?
We started by creating a URDF file from the 3D model of the AMS, and the URDF file allows ROS to create a simulation of the robot as a physical object. Then we tell the simulation how the joints are supposed to move and what the specs for the actual actuators are. Now, when the simulation is brought to life, commands are generated for the actuators to mirror the simulation, and the hardware interfaces translate these commands into the electrical signals that are ultimately sent. As this is happening, feedback on the motor's physical position is being sent and is reflected by the simulation.
So what were some of the challenges that we faced with using ROS?
Although ROS fits our needs, there were some challenges. No one on our team had particularly been exposed to ROS before, and the depth of knowledge needed to program a system so complex meant that only one person could specialize in it. In addition, many of the packages had poor documentation, and new knowledge required frequent redesigns and reiterations. By uploading our ROS scripts into GitHub and making our technical data package available, we hope to reduce the complexity for future teams and allow to iterate on our design without the need to develop a working system from the ground up.
Now that you kind of have an idea of what a robot is, I'd like to conclude by saying that we're pretty proud of our work, although we're not done yet. As of recording this video, we still have to test the robot walking, and that's why you're not seeing any video of that. However, we have inspected our robot and found that it does meet the height requirements, that it does meet the weight requirements, and many of the subsystem and system requirements have been tested and verified. We hope to see you on Design Day so that you can see this walk and see how it actually works. Until then, this is the Autonomous Mechanical Spider team, and thank you for your time.